To illustrate the Boltzmann formula and the associated concept of microstates and configurations, we are going to examine the partitioning of ideal gas molecules in two connected vessels, A and B, of identical sizes. Our goal in this exercise will be to understand why n particles tend to distribute themselves equally within the two containers if these have equal size. We start our discussion with the partitioning of two particles named A and B. We can readily see that there are four possible cases. That is, four possible microstates. Microstate 1 corresponds to the situation where both particles A and B are in cavity A. For microstate 2, particle A is in cavity A and particle B in cavity B. Microstate 3, particle A is in cavity B and particle B is in cavity A. Finally, for microstate 4, both particles are in cavity B. While we can envision four possible microstates, we also know that particles don't have a name and are indistinguishable. What this means is that we can only distinguish three different situations or configurations, namely the two extreme configurations where there are two particles in one container and zero particle in the other, and the configuration where there is one particle in each container. On this slide, we have named these configurations as 2, 0, 0, 2, and 1, 1. Since the particles in an ideal gas do not interact with one another, there is no reason to believe that some microstates should be more likely than others. The probability for each microstate is therefore a quarter, or 25%. On the other hand, we see that configuration 1,1 is twice as frequent as either configuration 2,0 or 0,2. We conclude from this study that placing two particles in two containers leads to 4, that is 2 to the power 2 microstates, and 3 configurations. We also concluded that the most probable configuration of the system, 1, 1, is twice more likely than the least probable configuration, 0, 2 or 2, 0. We now examine the situation where we have to distribute four particles named A, B, C, and D in the two containers A and B. Following the same reasoning as on the previous slide, we can define a total of 16 microstates. These microstates can be grouped in 5 different configurations: 4, 0, 3, 1, 2, 2, 1, 3, and 0, 4. For the sake of clarity, only the first 11 microstates were specified on the slide. You can easily write the remaining 5 microstates associated with configuration 1, 3, and 0, 4. Again, while any microstate is as likely to be observed as any other, the most probable configuration of the four-particle gas system is that exhibiting two particles in each container. This 2-2 configuration is actually 6 times more likely to be observed than the least probable configurations 0,4 or 4,0. As the number of particles increases, the probability of the most probable configuration increases and that of the least probable decreases. We now consider the case of a very large number, n, of particles to partition in the two containers. Let us first discuss the number of microstates. You may ask yourselves where these numbers of microstates, 16 for 4 particles and 4 for 2 particles, came from. The number of microstates is the total number of ways to place our particles in the two containers. For a system of 2 particles, the first particle, A, has 2 choices, A and B, and the second particle has also 2 choices, container A and container B. Hence, for a system with two particles, they are 2 times 2, or 2 to the power 2, that is 4 microstates. For a system of 4 particles, the number of ways to place 4 particles in 2 containers is 2 times 2 times 2 times 2, or 2 to the power 4. So if we place n particles in 2 containers, the number of microstates must be 2 to the power n. Now calculate the number of ways to place L particles in cavity A and R particles in cavity B, such that L plus R is equal to n. Well, this is a very common problem in probability theory. The total number of ways to place L out of n object is simply n times n minus 1 times n minus 2 times n minus 3 and so on until n minus L plus 1. Indeed, there are n choices for the first object, n minus 1 for the second, n minus 2 for the third, and so on and so forth until we pick the nth object, for which there are still n minus L plus 1 choices remaining. The total number of choices, which we would write as n times n minus 1 times n minus 2 times n minus 3, and so on and so forth until n minus L plus 1, is equal to factorial n divided by factorial n minus L. In our calculation, because the objects were picked sequentially, it implies that the objects are actually distinguishable from each other. Since in reality they are not, the quantity factorial n divided by factorial n minus L is actually an overestimate. To obtain the number of interest, we need to divide factorial n over factorial n minus L by factorial L, the number of sequences of L objects. The quantity factorial n divided by the product of factorial n minus L and factorial L is called the number of ways to combine n objects into groups containing L and R equals n minus L objects, irrespective of the way they are ordered in each group. So, the probability that a microstate has L particles in the left container and n minus L particles in the right container is the ratio of factorial n divided by the product of n minus L factorial L factorial to 2 to the power n. This number can also be viewed as the fraction of the microstates that have L particles in the left container and R, which is n minus L particles, in the right container. We can use this formula to calculate the probability that the microstate has the same number of particles in the left and right containers. That is the fraction of microstates where L equals R equals n over 2. This number turns out to be equal to 1 divided by 2 to the power n times factorial n divided by the square of factorial n over 2. With a little more math, we can show that this number approaches 1 when n is large enough. For microscopic samples of gas, where the number of molecules is on the order of Avogadro's number, n is certainly large enough for this result to be correct. So, our description of a gas sample partitioned between two identical containers as having the same number of particles in each container is totally consistent with the concept of entropy, which suggests that the microscopic state of a system at equilibrium is best described by the configuration of the system that exhibits the largest number of microstates. This observation also suggests that when describing a system at equilibrium, we often can ignore the configurations of the system that are not dominating, as for instance, the configurations where the number of particles are different in each container. It also suggests that to calculate the entropy of a system at equilibrium, we can often equate the number of microstates W of the system with the number of microstates in the most probable configuration. Finally, we can conclude that the properties of a system at equilibrium are the properties of the most probable configuration of that system.